So the code, let's get into this. I'm going to, let's see, get right here. So the first thing we want to do is we're going to import a couple of libraries. Now, these are going to be standard Python libraries. So we're going to do from typing. So we're going to strongly define a lot of the different types of variables that we're going to work with. This is for the sake of example. Now, if you're actually writing the code in an interview, you don't need to do this, but this is to get the most concrete example on paper that we can. So from typing, import list and tuple. Then we say from random, import. Now we're going to define our class, my linear regression. First, what we're going to do is we're going to initialize our linear regression. So in Python, you have to do a dunder init method, stands for double underscore. We take in the self parameter. We're going to take in two additional parameters for basic linear regression. We're going to take iterations, which is going to be an int, and we're going to take in learning rate, which is going to be a float. All right. We're also going to set default values for these because there's no need to pass them in every time if we can have some defaults. So we're going to say 100 iterations and a learning rate of 1. We're going to define self.iterations as iterations, and we're going to define self.learning rate as learning rate. Next, we're going to also define some parameters. We're just going to get some very initial ones down on paper. A couple of these will depend on the type of data passed in or if data is passed in at all. So let's just put down some default values for now. Self.intercept equals 0. So that's going to be the y or the beta naught. And we're going to say self.weight vector. This is going to be betas 1 through beta n. And we're just going to say it is a one-dimensional list as of now. And then we're going to say self.trained. So this is just a convenience thing. So we say it's not trained yet. We've just initialized it, and we have not yet called the predict function, or sorry, the fit function. Now what we're going to do is define initialize parameters. Or let's take a step back, actually. We're going to define the fit function. So this is what we want to call. We want to fit and to predict. And any other function that we define past that is going to be a helper function for fitting or predicting on our data. So we're going to define fit. So fit will take self, as all Python methods do, class methods. We're going to take in x, which is going to be a list of floats. So this is going to be our data vector. And then we're also going to take in y, which is going to be a list of floats. And it's not going to output anything, so you don't need to put any arrow at the end. So first, what we want to do is just a sanity check. We want to make sure our data is the same length as the y vector. So we're going to say assert length of x equals length of y. Okay, if that fails, then you can't really keep going. So now we're going to say, let's figure out the size of our data. Rows and columns equals the length of x and length x 0. Okay. Now we're going to define two more things. We're going to define intercept, which we're going to initialize our parameters. So we're going to define it and weight vector. And these are going to be defined by self.initialize, parameters. And we're going to take in our x and our number of columns. So we don't have initialized parameters defined. So let's do that. Initialized parameter is going to take in self. It's going to take in x, which is, again, a list of floats. And then it's going to take in columns, which is an integer, the number of columns we have. So for initialized parameters, our intercept, self.intercept, right, whatever we initialize it at, our weight vector is going to be random.random. Okay, we're going to put a random value in there. Generally, this is done with any kind of gradient descent. You want to start with a random value. Now, of course, it's hard to predict what range that random value should be in, so we're just going to use a simple range for now, whatever random.random gives us. And we're going to say for underscore in range columns. Okay, so what does this do? This makes sure that the weight vector is same length as number. That's why we use range columns. So here, the underscore is just so we can do a list comprehension, but the variable doesn't matter. And we're just going to create a random integer, or sorry, a random value for every single column that we have. And now we're just going to return intercept and weight vector. So the way you can represent this with Python typing is you can say we're going to return a tuple, and that tuple is going to have an integer and a list of floats, which of course this right here is. Okay, so now that we have our initial parameters set up, what we're going to do is we're going to define the training loop. This is where the machine learns. All right. So we're going to say for or let's do it differently. We'll do iteration number equals 0. I say while iteration number is less than self dot iterations. So this is done so that we can break out of the loop early, and I think it just reads a little bit better. So in case you want to do any kind of early stopping or stuff like that, you can easily update this style. Again, not really going to be used in our example here, but just to keep in mind. So now what we're going to do is we're going to get the prediction and derivative for this. Sorry, wait a minute. Mixing that up. I'll edit that out. So now what we're going to do is get the intercept gradient and the weight vector gradient. We're going to get those from self.compute gradient. And this function is going to take an x, it's going to take an y, it's going to take our intercept, our current intercept, it's going to take our current weight vector, going to take in the number of rows and number of columns. All right, so let's define this function. Gradient, self. We already know what types these parameters are, so I'm not going to define it right now. Now we have compute gradient. We're going to do the following. We're going to initialize the intercept gradient and the weight vector gradient. Let's say the intercept gradient is 0, and this weight vector gradient is going to be 0 times the number of columns. Okay. Now we are going to, for I in range rows, we are going to, so this code can be a little bit tricky, and I want to make sure that everyone understands exactly what's going on here. So we're going to do this for each data point. That's what we're doing here. Each row represents a data point. We're going to say yi hat. So yi hat is going to be the prediction of that data point I. This is without knowing the actual answer. So we're going to say yi hat equals our current intercept plus the sum of xi. So xi here is the the current row that we're concerned with, the entire row. Now we're going to say xij, so j is going to be the current column, okay, times weight vector j, okay, weight vector j for j in range columns. Okay, so let's make sure that this is all correct. Sum of this. Okay, should be right. So let's break down what we're doing. This again is your y equals mx plus b, but in the generalized form. So this is going to be your intercept beta naught plus the sum of each feature in this particular row times the weight of this feature in the feature weight vector. So now that we add all of these together, we get our prediction yi hat. Now we're going to compute the derivative of error. So the derivative is defined as 2 times the yi minus yi hat. Derivative 2 times yi minus yi hat. So this is going to be your residual. 2 times that is the derivative in a linear regression. Now we're going to, let's define that right here. So we're going to get prediction and derivative of this data point. Remember, here this is just a prediction and derivative for a single data point or single row. Next, we're going to partially update gradients for this data point's contribution. So we need to create our gradients, and we don't create the entire gradient at once. We update the gradient with the error from each individual row, and we just take that row's contribution and add them all up together to get the final gradient for the whole data matrix, if that makes sense. So let's just do that. Here we're going to say for j in range columns, and we're focusing on just the features. We're going to say weight vector j plus equals. We'll always use plus here because the gradient can be positive or negative, so we're just adding a positive or negative number. We don't need to worry about the sign. Derivative of error that we just computed times x I j, right? So we're still within this loop, so we can take the I and we're still doing j, and we're going to say plus, or sorry, divided by number of rows. So dividing it by the number of rows is just for getting the average. And here, the derivative times xij will get you the weight update for, or sorry, the gradient contribution of just this one data point. Okay, so now we also have to worry about what the intercept does. Do we update the intercept up or down? We'll define that. Intercept gradient plus equals derivative of error divided by rows. All right. So now we're going to return our intercept gradient and our weight vector gradient. So just to make sure everyone understands, here we're going through each row. Once we go through each row, we're partially updating every column for that row's contribution. We're going to end up updating each column the number of times equivalent to the number of rows we have. So if I have 100 rows, I'm going to update each column 100 times, and it's going to be 1/100th of that column's contribution, therefore taking an average. Okay, so now we have our compute gradient function. So now that we've computed the gradient, we are going to update our parameters. So now we're going to say intercept vector equals self.update parameters. And here we're going to take the intercept. We're going to take the intercept gradient. We're going to take the weight vector, the weight vector gradient, and we're going to take, that should be it, actually. Okay, so let's define this. Now update parameters of self. Okay. Now we have to say this equals okay. So the intercept is going to be intercepted by the intercept gradient that we just calculated plus the times learning rate. So learning rate is going to be the magnitude of which each of these gradients affects the next iteration. And of course you know that. So now we're going to say for I in range length weight vector. We're going to say weight vector I plus equals the weight gradient I times the learning rate. So again, same principle, but we're going through all of the different columns. In fact, we could use J to make it a little bit more consistent with the other methods. Okay. Okay, so now weight vector I plus blah, blah, blah. Now we're going to return our intercept and our weight vector. Awesome. So remember, these right here should always be plus because we just want to add the positive or negative derivative, or sorry, gradient. All right. Now that we have that, last thing we're going to do is we're going to say self.intercept equals intercept. So it's going to be the final intercept where we're just setting these parameters in stone. Intercept, we self.weight vector, weight vector, and we're going to say self.trained equals true. All right, so let's go over conceptually what this does one more time. We're going to define a fit function. We're going to make sure that our data has same directions, same number of rows at least. We're going to define rows and columns. We're going to initialize our intercept and weight vector with this initialized parameters function. We're going to just use the intercept that we defined because an initial intercept of 0 is fine. Then we're going to also do a random initialization for every single column that we have and return those. We're going to go through our iterations defined by the number of iterations we initially passed in. We're going to compute the gradients. Then we're going to update our parameters. Then we're going to, once we're done, finally set our self.intercept and self.weight vector based on what we calculated. Awesome. All right, everyone. So now the last thing we want to do is define a predict function. Predict will be here. We're going to take in an X matrix. So it's going to be list of floats. And we're going to want to output a Y prediction vector, which is going to be a list of floats. How are we going to do this? First, we have to assert that the length of x0 equals the length of self.weight vector. Here, we're just making sure that the number of columns that are being passed in our new prediction matrix is the same. Otherwise, if it's a different shape, nothing's going to work. Also, we're going to assert that self.trained equals true. In Python, you can just do self.trained. Ypred is going to be our output vector. So we're going to define that as a list of floats, and we're just going to initialize it like this. Oops, type that in. All right. Now we're going to say observation is a integer. Sorry, is a list of floats. We're going to say for observation in X, we're going to do the pairwise feature contribution. This is going to be a list of floats. This is just going to be a vector with the weights that we have times the actual numbers that were given in this observation, in this particular observation right here. So list of floats equals, we're going to say A times B for a B in zip self.weight vector and observation. So if you don't know what any of these do, I would encourage you to just look them up. This is called a list comprehension, and we're just multiplying the weight, which is A, the observation feature number, which is B, after we have combined them into a single list of tuples. Next, what we're going to do is ypred.append, and what are we going to append? We're going to append our prediction, and our prediction is self.intercept plus the sum of the pairwise feature contributions. Feature contribute. All right. Pairwise feature contribution. Awesome. And now at the very end, we're going to return y. Right. Perfect. And that is how you code up a linear regression. If you need to do pseudocode, you can always just kind of loosely define some of this stuff. But if you need the actual code, this is how it works.